Welcome to our final keynote for this virtual Interspeech. Our speaker today is Shahzad Mevawala from Amazon. Shahzad is responsible for speech recognition, speaker recognition, and paralinguistics in Alexa worldwide. Alexa, of course, is the conversational assistant that has pioneered the use of far-field speech recognition for smart speakers. And in his talk, you will hear about the technology that makes these devices tick. Shahzad is a 13-year veteran at Amazon, where he was in a variety of senior technical roles prior to Alexa, including supply chain optimization, marketplace trust and safety, and business intelligence. Before joining Amazon, he was director of software at HNC, a financial AI company, where he worked on products that use neural networks for detection of fraud. Shahzad holds a master's in computer engineering and a bachelor's degree in computer science, both from the University of Southern California. And now, Shahzad, take it away.
Hello, everyone. My name is Shahzad Mevawala, and I am the Director of Speech Recognition for Alexa. My team consists of scientists and engineers who are responsible for developing the technologies to help Alexa hear the customer, namely speech recognition, language identification, speaker identification, and paralinguistics, and this is worldwide. I would like to start by first thanking the distinguished organizing committee for giving me the opportunity to speak with you about Alexa. Today, I hope to provide you with a behind-the-scenes look into the technical complexities as well as the science that goes into building and running Alexa. So with that, let's jump right in. We will first spend a few minutes talking about the origin story of Alexa, followed by an architectural overview. From there, we will focus on a small selection of speech science-related topics that are instrumental for Alexa. I will be focusing mainly on ASR and related technologies, but will provide a broad brush for the various other components in the system as well. We will talk a little bit about more natural interactions enabled via paralinguistics and speaker recognition, dive into edge processing, and then wrap up with a look to the future. So how did Alexa come to be? Inspired by the computer on Star Trek, a team of Amazon scientists and engineers set out to build a computer in the cloud that could be completely controlled by voice. This voice experience could then be built into everything and be available everywhere. As Amazon started to build out its speech team, we also consulted with several experts in academia. The project itself was, of course, secret at the time, so no real details were on offer. However, what we heard over and over again was, whatever you do, don't work on far field. Far field, of course, was the key enabling technology and the core reason for Alexa's success. These efforts led to the launch of the first Echo device in November 2014, and with it, the creation of the smart speaker category. At launch, we had 13 skills from one developer, namely Amazon, one device, and one language, specifically US English. Today, we have a device for nearly every situation, with and without screens, and even on the go. For example, Echo Auto, Echo Buds, and Echo Loop. And these are just Amazon devices. There are more than 100,000 Alexa-enabled devices in the market with availability in 15 locales. Now imagine a world where more than 100 million devices are all connected to Alexa. Imagine thousands or tens of thousands of utterances being spoken to Alexa every second, billions per month. Then imagine a system that has to process all these requests in real time with near instant responses. But it is even more challenging than that. Consider that each of these billions of utterances are split into 10 millisecond chunks, such that each second of speech now consists of 100 frames. Each of these frames must be scored through a compute-intensive ASR deep neural network. The scale of the problem becomes even more clear. Let's look at a peak scenario. Imagine a scene Christmas morning. Millions of Alexa devices that were bought as gifts all light up together between 7 a.m. and noon local time in each locale. Imagine a rolling window where these millions of devices come online together, all for the first time. We must delight our customers, especially on Christmas Day. Now imagine other holiday celebrations across the world where this scenario is repeated. Each one of these utterances must run ASR, speaker ID, language ID, whisper, natural language understanding, entity recognition, domain routing, skill execution, text-to-speech, etc., all within a minimal response window. Imagine also the system has to be up 7/24 with 100% availability. For example, if ASR were to go down, what would happen? Well, Alexa is a speech forward assistant. If ASR were to go down, all of Alexa would be down, which simply cannot happen. So what does it take to build a system like that? What does a system like this look like? Let's take a bit of a closer look. First, let's take a look at the high-level workflow of Alexa. There are basically 4 stages. The customer invokes Alexa and starts speaking to it. Alexa is listening. It then processes the request and it responds. Seems pretty simple, right? In reality, each of these components employ millions of lines of code, hundreds of subsystems, and multiple machine learning models each. A simple utterance like a weather query, Alexa, how's the weather in Shanghai today, must be properly converted to text via a call to ASR. Next, natural language understanding must get the intent right, weather, and entity recognition must resolve the slot, Shanghai. It must get routed to the right skill, in this case, weather. The weather skill must retrieve the weather forecast and provide the textual response. TTS must then render this response in Alexa's natural voice. And all of this must happen in a flash. Let's dive a little deeper into ASR itself. Once a customer activates a device via the wake word, audio is streamed to the cloud, arriving at the network gateway. An audio distribution framework then routes the audio to the services that need it, including ASR, language ID, speaker ID, whisper, etc. All these functions must run in parallel, otherwise latency would be too high. But of course, there are thousands of simultaneous requests hitting the system. As a result, we must have a multi-fleet system with thousands of AWS hosts spread across multiple regions. Fully redundant availability zones must be present for each service to ensure that the system is always available. This all must be streaming, so we cannot leverage bidirectional models or any other such offline constructs. There's also no frame look ahead so as to minimize latency. Each utterance is on the average of 3 to 5 seconds in length, and each one gets split into 10 millisecond frames. The service itself is bidirectional so that when the endpointer determines the end of utterance, the audio stream can be terminated immediately. Now let's take a look at some of the science that is behind Alexa. At Amazon, we are always customer obsessed. It is part of our ethos. We start with the customer and work backwards from them. Alexa must therefore work just as well for all of our customers worldwide. This means that our ASR models have to adapt to not only different languages, but different dialects, vernacular, trending topics, accents, native and non-native speakers, and multilingual speakers. In addition, this is a touchless device. There are no correction capabilities. There is no backspace or feedback possible in that single utterance. We either get it right or we get it wrong. And under all these constraints, we must provide the same great performance for all. What kind of science and innovation does that require? Of course, many of you know about or are experts in core language technologies like ASR, natural language understanding, and TTS. But putting them together in a system of this scale and generalization is a very big challenge. Customers should not have to adapt the way they speak to match our capabilities. They should be able to interact with Alexa in a way that is natural to them. Let's take a look now at some of the challenges and the solutions. Have you noticed that Alexa can focus on the person speaking, even in the presence of background speech or media noise? How does this attention and filtering work? Typically, ASR is trained on the speech segments only. However, there is additional context available as related to the speaker, channel, and environment that can be used to enhance performance. This context is typically untranscribed and must be learned implicitly. To use untranscribed audio context, we actually encode the entire stream, but compute loss only on the transcribed segment. However, you backpropagate over the full utterance. This allows the system to implicitly adapt to the speaker and the environment. This allows ASR to focus on the speaker that invoked Alexa. The accuracy improvements are particularly pronounced in the presence of background or multimedia speech interference, as can be seen in the table below. Alexa must also be highly performant regardless of noise, device type, accents, and dialects. Semi-supervised learning is particularly effective in helping to overcome these challenges. With SSL, we use a smaller amount of label data to train a teacher model, which is then used to label a much larger store of unannotated data. We then use both data sets to train a leaner, more efficient student model. Let's get into some of the details of this. A teacher acoustic model, which is a powerful bidirectional LSTM, but is not suited for streaming applications, is first trained on label data. This teacher model provides a 25% word error rate improvement over the streaming model and is therefore well suited for the task. Labels for a large quantity of previously unlabeled data are then machine generated using the teacher model. You will notice in the diagram both pooled and locale-based data. We will discuss these in more detail in our next slide. For CTC SSL training, machine labels are generated by first post-processing the teacher's posteriors obtained by forward pass. The label sequence is obtained by taking the argmax over the teacher posteriors and then removing consecutive repetitions. A student AM, which is a unidirectional LSTM, hence suited for streaming applications, is then trained on both labeled and unlabeled data. This is a much faster approach than running a full decoding, especially when data volumes are very large. Next, we combine SSL learning with transfer learning, which proves to be extremely powerful. In this approach, we pool transcribed and untranscribed data from multiple languages to enhance a single language. In this example, we show variants of English, but it can be effectively applied to a mix of different languages as well. The diagram on the top shows a multi-dialect acoustic modeling training pipeline based on label data only. It consists of 3 stages. The pooled CTC label data from the 4 variants is first used to train an overall English model. Then a locale-specific CTC training is applied using only the data from the target locale to fine-tune the model. This is then followed by locale-specific discriminative training. The diagram at the bottom represents a multi-dialect acoustic model pipeline based on both labeled and unlabeled data. In this, we combine 75,000 hours of labeled data with more than 1 million hours of unlabeled multi-dialect English data and leverage it to improve all three stages of acoustic model training: the pooled CTC-SSL, the locale-specific CTC-SSL, and the locale-specific discriminative training. The SSL data to be labeled can be made a lot more effective by careful automated selection based on confidence filters and speaker and domain diversity. This table shows us the accuracy improvements from the techniques we just discussed. The full combination of all techniques resulted in a 22% to 29% improvement in overall word error rate over the baseline model. Let's talk a little bit about rescoring. Generalized neural language rescoring models are very effective for re-ranking the output of the first pass ESR system. However, a general model does not take full advantage of the context that is available. For instance, is the domain or topic of the utterance related to shopping, navigation, or music? With domain-aware rescoring, we use an intent classifier to guess the domain of the utterance. We can then use domain-specialized re-rankers to extract the best possible result. Even though the precision and recall of the classification exceeds 90%, these specialized models must still be robust to classification errors. As you can see, we can get significant word error rate improvement over just a generalized rescorer. The general rescorer also just uses the lattice in order to re-rank. However, adding attention to audio provides additional context for discriminating between alternate hypotheses, leading to a 7.7% improvement in word error rate. These language models are also hard to adapt. Personalization of entities like contact names or playlists are essential to correct recognition. New catalog entries for songs and movies are equally challenging. These also have to scale across millions of users and must support very frequent updates. The answer lies in composite models. The set of entities that a user may reference is constantly growing or are dependent on the user and the application. For example, for a communications application, we need to pull names from their list of contacts. For many other scenarios, we need global catalogs, for example, geographical locations. Or an app may provide the entity list for its own purposes, such as the characters of a TV show or rooms in a home. We want the LM, the language model, to access these lists of entity names, but how do we know when to invoke them? The standard solution is to build language models in terms of class labels, such as location. The language model predicts the class, then we have a separate model to predict the possible class members given the type of class. The membership models can be context dependent or personalized. However, to train class-based models, we need those classes or entity types annotated in our data. Annotating significant amounts of data is very expensive, and adding new classes would require relabeling old data. And in the case of third-party applications, where each application can have its own entity types, it's not very clear how to scale the labeling process. Also note that in this example, the location in the sentence is my hometown, while the entity model only contains hometown. The annotation process itself can introduce discrepancies. Can we do without these animations? It turns out that we can. The basic idea is to let a neural model learn the context under which different classes become good predictors of words. We have a set of component models that can generate words, but some generate only specific entities. Let's take a communications interaction as an example. Alexa, call Shahzad Mevawala. We want to leverage the user's personalized contact list to guide and personalize the second pass neural LM rescoring. We combine the components predictions using an attention mechanism. But we also have to learn which models are good at generating particular portions of an input query. For example, a personalized contact list slot is not really good at generating words from the carrier phrase in our example, Alexa call, but are good at generating slot words, Shahzad Mevawala. The model learns which component model should be activated at particular positions of a query, and in addition, which models are good at predicting next word and position based on the context. We use a context encoder to make a fixed size representation from the sequence of previous words. This is the query in the attention mechanism, but also the input to guide the activation component to help with the learning as to which model should be activated at any position. This is matched against the learnable embeddings that represent each component model. These serve as the key in the attention mechanism. The attention mechanism computes the weighting of the different component predictions according to the match between the queries and the keys. So far, this is just context-dependent interpolation of models, but some components can generate only parts of a sentence. They need to be told when to start generating their content. We use a novel mechanism we call activation, which resets the state of a component to tell it to start generating its content. Activation is also computed by matching context queries against component keys, but each component decides independently and probabilistically when to activate. For training the activation model, we use reinforcement learning. There is no need for label data because backpropagating the errors allows the model to learn when to call on each component based on context and what the component predicts. We applied the neural composition model to combine a default language model with personalized contact lists for communication tasks. On in-domain utterances, perplexity was cut in half, and recognition improved by 10% relative. No degradation was found on out-of-domain data, so the model learned not to pay attention to the contact name component in those cases, even without training on labeled data. For far-field applications, interactions are usually explicitly triggered via invoking the wake word. But termination must be computed by automatically inferring when a user is done speaking. End too early and you may cut off the speaker. Wait too long and you add latency or risk introducing unintended insertions. The system must learn to respond instantly at the end of a spoken query, but also be patient if the user hesitates or pauses during speech. Endpointing uses no explicit feature extraction. We instead fuse multiple signals, including acoustic embeddings, for example, silence, one best hypotheses from the ASR decoder, as well as expected pauses based on the linguistic position within the sentence. We also want Alexa to effectively use features beyond just speech recognition in order to enhance the overall customer experience. Whisper is a great example. When you whisper to Alexa, she will whisper back. That is a magical experience for customers. For example, when you set alarms late in the evening while your family is sleeping, or when you're checking calendar, weather, or traffic early each morning while others are still asleep. The Whisper feature allows Alexa to understand that this is a quiet environment and behave like humans would do. Whisper speech is mainly characterized as unvoiced speech. Studies of spectrograms have suggested that whisper speech overall has less energy at lower frequency bands compared to normal speech. We came up with a system that consists of an LSTM neural network trained and evaluated on recordings of human interactions with voice-controlled far-field devices in whisper and normal modes. But it's not just about the science on the detection side that makes this feature magical. We were also able to create a comfortable whispering voice from text-to-speech in response. The response in kind is what makes the experience magical. If you allow Alexa to recognize your voice, she can greet you by name and personalize your experience. For example, music playlists, shopping carts, etc. Speaker enrollment commences with the user speaking 4 short phrases. We designed these phrases not just to be simple and topical, but also to provide the greatest phonetic coverage, allowing us to deliver the best recognition accuracy. Alexa's Speaker ID system uses a combination of 2 different model types. The text-dependent model knows what you're saying ahead of time. With Alexa, most utterances start with the wake word, so it matches the way you said Alexa now with the way you said Alexa before. Then there's the text-independent model, which matches your voice regardless of what you're saying. Moving both these systems to full neural and combining them has given us an order of magnitude improvement in speaker ID accuracy. Instead of fusing the decision scores of multiple models, for example, a straight average, we fuse the embeddings generated by the component models, which are all neural. This allows us to let the model learn to estimate any missing embeddings from the ones that are present. For example, if the utterance did not start with a wake word. This neural fusion method gave up to a 15% relative reduction in overall false reject rate. And when one of the inputs is missing, the false reject reduction was up to 53%. Now, let's switch topics and talk a little bit about edge processing, or processing on the device itself. When you're processing on the cloud, you have an unlimited amount of computation power to run the powerful machine learning algorithms that are required for voice assistants. Now imagine you want to fit this functionality and squeeze it into a device no bigger than a tin can. You have almost no memory, megabytes instead of gigabytes, a fraction of the compute, and no dedicated system resources. How does one accomplish something like that? In the latest Amazon devices, we've incorporated our new AZ1 Neural Edge Processor, which is a neural network accelerator that allows us to run these sophisticated ML algorithms efficiently and quickly right on the device. This neural processor will allow us to move all audio processing to the device. Current Echo devices listen for the wake word on the device, and once detected, they stream audio to the cloud for all further processing. These new devices give us the capability to execute ASR, Speaker ID, and Whisper on the device itself, such that only a textual representation needs to be sent to the cloud. This means faster response times, especially on narrow bandwidth connections. Let's now review for a minute how classic hybrid ASR architectures work. A hybrid ASR system is comprised of multiple components. A signal processing front end takes raw audio frames as input and produces a stream of feature vectors that serve as inputs to the acoustic model. The acoustic model then produces phoneme probabilities for each given frame. The decoder then combines the phoneme predictions with the pronunciation lexicon, as well as the n-gram-based language model to execute a large search over all possible combinations of words to find the most likely sequence. These multiple components, when packaged together, especially when inclusive of the large language model, results in an extremely large overall ASR model size. These components are replaced when moving to an end-to-end architecture. The technology we adopted and extended for all neural ASR is commonly referred to as RNN transducer or RNNT. It consists of an encoder network that transforms the audio signals into a new frame-by-frame representation over time. A prediction network that encodes the respectively current word sequence, and a network that brings both pieces of information together to yield probabilities for all potential next words or word pieces. With an end-to-end model, you no longer have the overhead of the various separate components or those giant search trees. Instead, you now have a full neural representation, which by itself reduces the size of the model to 1/100th the original size. Various quantization techniques minimize the memory and compute footprint even further without losing any accuracy. These models can then be deployed on our devices and executed using our Amazon neural processor. But what about even smaller devices like wearables or automotive applications? Some of these may not even have internet connectivity. One of the techniques is obviously model compression and quantization. Quantization helps to reduce model size, computation, and latency. The main problem is that post-training quantization leads to severe performance degradation. To achieve the best performance on device, we need to incorporate the hardware architecture into the model training itself. With this solution, we were able to reduce the model size by 4x without degrading the performance of a speech recognition model. Furthermore, this solution requires minimal overhead for memory and computation, which makes it well suited for models with a large number of parameters, such as speech recognition or even text-to-speech. Another approach to reduce footprint and latency are signal-to-intent models. The conventional approach to spoken language understanding uses two different components to sequentially process a spoken utterance. The ASR model first converts the customer audio to a text transcription, followed by the natural language understanding model that converts this transcription to a semantic interpretation. This approach has worked well so far, especially with the adoption of neural technologies for both ASR and NLU models. However, this modular design has a few drawbacks. The component models are trained independently with separate objectives. Can be word error rate for ASR and cross entropy for NLU. The errors made by the ASR model can lead to an incorrect NLU model prediction, since these errors are absent from the NLU training data. Finally, this design assigns equal importance to each word. In the three examples shown here, the word error rate for each utterance is 25%. However, missing a keyword from the utterance will lead to a non-recoverable NLU error. The word error metric does not differentiate this effect when looking at the final model performance. An approach to address this problem is to employ models that can predict the spoken language understanding output directly from speech. These end-to-end SLU models are trained on a single optimization objective, that is, to correctly predict the utterance interpretation. These models are robust to component-specific errors. Moreover, they are resource and latency efficient. Instead of having multiple models to get the final interpretation, we now have a single model, often with fewer total number of parameters, that can predict the final interpretation. This finally leads to smaller sizes and overall less computational overhead. Looking a bit to the future, virtual assistants are still early in their evolution. They work really well for command and control type interactions, controlling smart home devices, answering questions, playing music. Where we really want to get, though, are true conversational assistants. Alexa's natural turn-taking feature, which we plan to launch next year, will let customers interact with Alexa more naturally without the need to repeat the wake word. The feature's AI will be able to recognize when users have finished speaking, when the speech is directed at the device, and when it is not, and whether or not a reply is expected. Natural turn-taking uses acoustic cues to distinguish device-directed and non-device-directed speech. It adds other cues such as visual information from devices with cameras. On-device algorithms process images and audio, infer from the speaker's body position whether they're likely to be addressing Alexa, and infer from the audio whether it is directed to the device or to someone else. We still have many challenges to solve: self-correction capabilities, code switching, interpreting paralinguistic cues from customers, and true high-fidelity, long-form conversational ASR are just some examples. Though it has evolved over several decades, thanks to steady progress in academic, government, and industry research, speech technology has seen rapid progress over the last few years. This is thanks mainly to deep learning algorithms, as well as the low-cost compute hardware necessary to support them. As we also saw in this presentation, building a virtual assistant requires the orchestration of several critical subtasks like wake word detection, endpointing, ASR, NLU, TTS, etc. And while we have made great progress, it is still day one and a great time to be a speech researcher. Thank you very much for your time and attention. I will now be happy to answer any questions that you may have. Sorry, can you guys see me? I'm sharing the video, but I don't see it. Question, so Amazon can now hear our whispers. Well, you have to be very close to the device, obviously. If you try and whisper across the room, it's not going to work, similar to how the humans would whisper to each other. So again, you still have to use the wake word to invoke Alexa. It works the same way, except now you can speak in a whisper instead of in a full voice. But that's the only difference. There's a question about unit selection and neural solutions for synthesis. I'm assuming you're talking about TTS here. So TTS is fully neural for Alexa as well, and has been since last year. Question on how do you get sufficient quantities of high quality audio to intent data to train an end-to-end audio to intent system? Well, As part of Alexa, we are in both supervised and semi-supervised fashion able to correlate the end-to-end pipeline. Since our pipeline runs ASR through NLU, we can tag the utterances that we get with the final intent that is computed using the standard approach, and then train the models based on that. On the question of how many devices are running hybrid ASR, how many running with RNNT, the RNNT functionality is upcoming. It hasn't launched yet. It will be launching very shortly. I don't have the numbers for you at this point. End-to-end approaches like RNNT provide many advantages. How about disadvantages? For example, adaptability with respect to domain change, which is the hybrid case, simply involves replacement of the language model. We don't really have the luxury of replacing the language model, even in the hybrid case. In the case of Alexa, it's a multi-domain environment. ASR does not know the topic ahead of time, and because it's streaming ASR, you can't reprocess it. So that's why there's the rescoring component, and we talked a little bit about domain-aware rescoring. And so the same technique applies to RNNTs as well, where you can do domain-aware rescoring. We also use shallow fusion in the RNNT as well to adapt the RNNT model as well. So there are some challenges. The RNNT model is a little bit more formed or less flexible, if you will, in being able to adapt. With an FST, you can simply add in components. With RNNT, it takes a few more tricks, like shallow fusion, etc. And then reliance on rescoring helps. Removing the dependency on the wake word will be much easier for the user, but presumably it increases the risk of privacy violations. You're correct. Removing the wake word can have that. There are mitigations to that. So number one, having all on-device ASR mitigates it to some extent, because you're no longer streaming voice to the cloud if that happens without a wake word. Secondly, the way that Alexa, the piece I talked about, natural turn taking, you actually have to invite Alexa to join a conversation. So it's not always in that mode. So you'd have to say, Alexa, join my conversation. From then on, it becomes automatic and without wake words. So it's invoked. And then from then on, you carry a conversation, and then you can terminate that conversation after that. So there are mitigations to that, and a way to reduce or eliminate those concerns. Why not personalize Alexa's voice, making Alexa speaking with family members? There are a lot of research topics. I don't know how many of you have tried the Samuel Jackson voice that Alexa launched. It's actually quite a fun interaction. For those of you who haven't tried it, there is also in India, Amitabh Bachchan will be launching soon as well. So we're definitely experimenting with that. I can't speak to future, but lots of fun stuff happening with TTS overall. Is Amazon correcting speech recognition errors automatically? Yes, we are in the background. Again, not my area of expertise. It's done downstream after NLU and ER are completed. But there are correction mechanisms that, based on most common errors, things like that, that will autocorrect as well. For how many and which languages will natural turn taking work? I do not know the answer to that yet. It's still very much under development. Our goal is to provide parity for our users across the world. We usually will start somewhere and then expand as we go. What are the challenges in bringing NLU and ESR in an end-to-end fashion? I think number one challenge is the breadth of NLU. As we combine it, it's currently suited for domains that are restricted domains. So for example, really good for applications like automotive, where you have command sets that you can target. That typically the main advantage of end-to-end NLU and ESR is to reduce the footprint on a device itself. Those types, but when you get into going for larger domains, I think there's still a lot of research to be done for that. The termination word, I think you're talking about the natural turn taking. Yes, you can actually terminate it, or it will auto time out after a while as well. Do you have plan to adjust Alexa voice to the accent dialect of the customer so that it's sounding more familiar? We have a number of voices all over the world, but right now, for in US, for US we have a voice, for India we have a voice, and so on. That has been the range. Again, I don't know the plans for TTS at this point, but we are definitely expanding in voices and locales as we go. We tried a number of architectures. There's a question, did you try using streaming attention-based encoder-decoder model? We tried a number of architectures, and then we settled on RNNT as that was providing us the best performance as well as compute signature. Can Alexa remember previous conversation context? For example, if I say, Alexa, tell me about it, will Alexa know what it is? It does. You can say, Alexa, how old is Barack Obama? How tall is he? And so that anaphora is maintained through on turns. So yes. One of the advantages of on-cloud processing is the data collection it allows. With on-device processing, this is not possible. Do you plan to use some alternative methods to do data collection? There are a number of methods. Obviously, federated learning is a method that can be used as well. Also, not all devices have the capability to do on-device processing because of the lack of compute power or whether you have the neural chip or not. In addition, we are still sending the audio to the cloud so that customers have a uniform experience across it, even though the audio processing happens on the device. When can we expect to see Alexa recognizing correctly code switching sentences for user selected sets of languages? That's a really good question. Code switching is a tough problem. We are at a point now where we do language identification. So you can, for example, in India, you can set your device to recognize Hindi or English. And Alexa can tell the difference between the two when you speak Hindi or when you speak English, and will respond in kind. Same thing for Spanish and English in the US, and a variety of combinations in Europe and Canada. But true code switching, where people mix utterances, is a harder problem. However, the good part is that RNNT is actually a very natural architecture that allows multilinguality as well. So that's something we're definitely experimenting with as well. Is your processing pipeline more or less homogeneous for all languages, and how do you deal with low resource languages? Again, good question. Our processing pipeline is homogeneous. Our goal is that regardless of the language, that our customers have the same experience and accuracy that any other language does. Transfer learning, as I'd mentioned in the talk, is a great resource for that. Semi-supervised learning is another really good resource for that, that allows us to use the learnings from other languages and adapt to the existing language. So we've made a lot of progress. Low resource languages, or especially languages that we've launched very recently, we are able to use transfer learning and semi-supervised learning to great effect for that. Clearly, command and control Q&A are very useful for users, but do users actually want less focused, more social conversations? I think it depends. Alexa gets a lot of what we call phatic utterances. So things like Alexa, will you marry me is a very common utterance that we see. But for situations where you really want to plan something, so for example, there's a really good video out there for natural tone taking, with trying to plan a night in, like what movie should we watch? Alexa, what's your recommendation? While we are waiting, can we order pizza? And as these two people converse, and Alexa has been put into that mode by saying, Alexa, join my conversation. Alexa helps by interjecting or picking up on cues and so on. So I think the capability is definitely there. I think before Alexa started, no one really knew that they needed a smart speaker that could even answer Q&A or do command and control. So I think we'll learn as we go and see what kind of scenarios really engage with the customers and which don't. Would you use a single ASR end-to-end model for multiple languages? Yes, absolutely. That's ongoing research work for us as well. I think especially in languages, in locales where there's a lot of code switching, that's definitely a great way to solve those issues. Is there an investigation into allowing Alexa to interact with more than one person at the same time? Yes, that natural turn taking is part of that, where you can join a conversation and multiple different people, so that that gets into speaker ID, diarization, cocktail party problems, etc. All have to be solved as part of that. Do you update your LM with time and cultural relevance? The LM of 2013 may not be suitable to answer the question words of 2020. Absolutely, our LMs are actually updated very frequently. There are catalog updates that happen. The LM gets rebuilt multiple times in a year, and it's kept up to date as new data flows in, and can be adapted very quickly. What are the current capabilities of training ASR models for many languages at once? I think I addressed this one. Yeah, I think that's further research work that we are doing, and RNNTs are a great architecture for that. Are there plans to implement some sort of federated learning? Federated learning is a great approach. It's definitely a great area of research for all research teams worldwide. For code switching, RNNT seems to be more promising than transformer. Do you agree? I do agree. It definitely has that capacity, and I think is very promising initial results from it. Has there been any noticeable change in Alexa usage as a result of the COVID-19 pandemic? More people are at home, so interactions with Alexa, there's more opportunities for that. I think there have been things that have changed are, people set less alarms because they're home, and they're not, but the Q&A aspect of it goes up because people want to know about COVID-19 and so on. So yeah, so there have been changes in pattern in usage, I would say, but overall, I think not so much in terms of accuracy or anything like that. That hasn't changed much, but how they use it has shifted slightly, I would say. Is there an effort to make Alexa more human-like, or is it accepted that humans are okay with it being machine-like, since it's literally a voice from a machine? Well, we definitely want it to be more natural, and we want the ultimate thing you want to get to is a voice assistant that is unobtrusive and is there when you need it, and is able to handle interactions very naturally without you having to specifically say things in a certain way. I think we made a lot of progress there, but you always want the assistant to be an assistant, not a primary. How do you handle hesitations, interruptions, and interactions with Alexa? Is it slowly the responsibility of the ASR model? Actually, it is, yes. The endpointing technology that we mentioned has to be aware of the context and where you are in a sentence, and look for disfluencies like and and things like that in order to get the right transcription. Once the transcription is done, then the rest of the stack just works off of that. Is tone of voice a factor in conversational interaction? No, not really. I think if you, it's more of what type of environment you're in, whether it's a noisy environment or not, but tone is not a factor. How do you evaluate whether changes to the accuracy of the models impact the end user experience? A very small set of utterances are transcribed. We also have a confidence score built into our ASR model that is correlated with word error rate. So we can use the confidence scores and see how things have changed and how the model is behaving in the field. Does disfluency removal take place for language other than English? Yes, all languages should work equally well. Just looking for more questions that I haven't answered yet. Okay. Any more questions I can answer? I'm looking, I don't see any that I haven't addressed. This one says, so on the naturalness issues, have you considered that it being more natural in human-machine interactions for Alexa to have a more machine-like voice? Actually, based on when we switched our voice to all neural, we actually saw a rise in engagement. So it definitely, I think, helps users when Alexa does not sound as robotic, if you will. Talk about Alexa and the choice of keyword Alexa, and that's better suited for KWS tasks. I'm not sure what you mean by KWS tasks. So I don't know how to answer that one. What are the techniques that can be used to secure privacy in a smart speaker? Well, all the smart speakers that Amazon sells has mute buttons, and you can always turn it off. There is already a high level of wake word verification, etc., on the device itself. There are also settings that are available in the Alexa app where you can automatically delete your data. So you can have different retention periods to no retention period at all. So those are all techniques that are available. Thank you. How good is the emotional speech capacity in Alexa? I'm not sure what you mean by that, from a recognition perspective or Alexa able TTS perspective. If you could help me with that. Can you tell us what Alexa will look like 10 years later? I'm not sure, actually. That's a really good question. I can barely tell you what it'll look like in 2 or 3 years. Things are changing so quickly. Keep in mind that Alexa was just launched 6 years ago, and before that, this category didn't even exist, really. So so it's hard to answer that question. Okay, let's see. Can Alexa work with disordered speech? I'm not sure what you mean by disordered speech, but if you can help me with that, I can help answer. Let's see. Amazon always gave us great chocolates at Interspeech. Yeah, I was really hoping to be able to deliver this presentation in person, but it's strange times for us all, I think. To what extent is overlapping speakers problematic for Alexa? I think we discussed a little bit about how Alexa keeps focus, and it actually works really well. Now, obviously, I have 3 kids, and when my daughter tries to play, especially the Frozen soundtrack, the other boys suddenly start yelling at the top of their voices to prevent Alexa from hearing. So yeah, that can be problematic. But in most cases, it works pretty well, actually. Kid speech recognition is more challenging than adult speech. Can Alexa also take care of disfluencies, hesitations in speech? This is more common for child speech. Yes, kid speech is definitely more challenging. And it's, again, an area of active research. I think kid speech is more challenging even for adults, I think, as for those of us who are parents, especially when kids are very young, we learn to understand our own kids, but when somebody else listens to them, it's hard for them to understand. I think it's the same type of thing. But we have some, the free time functionality for Alexa is a great companion or an addition for kids, actually. And then also we have this new Read with Alexa program, which we are launching soon as well, that allows kids to read with Alexa, where Alexa will read one page, the kid will read one page, and so on. And so we're definitely focusing a lot more on that, but it's definitely a difficult area. Dysarthric speech, not very well, I would say. I think that, again, an area of active research. We, as I said, we are customer obsessed. We really want Alexa to work for all of our customers. So it's definitely an active area of research. I think some of the issues around that are being able to get enough data to be able to train the models on some of the disordered speech issues, and be able to train our models to be able to understand that.
Professor, time is running out.
All right. Well, thank you very much, everyone. I really appreciate the time. I'm sorry my video didn't work. I don't know why, but I really appreciate all the great questions, and thank you very much for having me.